At the center of the galaxy M87 sits an object 6.5 billion times heavier than the Sun, firing a single beam of matter in one direction for longer than most stars have existed. That beam is not fed by anything falling into it. It is fed by the spin of the black hole itself, a wheel that never runs out of momentum to give away. Tonight, we follow that beam from the exact mechanism releasing it to a twin beam almost nobody has ever photographed. At the start of the 20th century, an astronomer pointed a telescope at a galaxy sitting inside the constellation Virgo and expected to see what every other galaxy showed: a soft haze of stars, dense at the center, fading at the edges. What he found instead was a straight line of light cutting through that haze, sharp enough to look almost drawn rather than photographed. A galaxy does not produce straight lines. Stars scatter randomly under gravity. Gas clouds curl and drift. Nothing in the ordinary physics of a galaxy produces an edge you could trace with a ruler. The galaxy was M87. The observer was Heber Curtis, working at Lick Observatory in 1918. He described a curious straight ray, faint but definite, connected to the nucleus by a thin line of matter. He did not know what it was. For decades afterward, the ray sat in astronomical papers as a footnote, sketched, occasionally re-photographed, never explained. A straight line inside a galaxy should have demanded an explanation immediately. It sat unexamined instead, and the delay says something specific about the year it was found in. 1918 came before astronomers understood that galaxies were separate island universes rather than clouds inside our own. It came before anyone understood that some galaxies harbor objects capable of releasing energy at a scale ordinary stars cannot approach. The photograph existed. The physics to read it did not exist yet. Starlight comes from nuclear fusion, and fusion produces a specific, well-understood spectrum. Look at the light from any star, and you can read off its temperature, its composition, its age, since the physics of hydrogen burning into helium is identical everywhere in the universe. The light from the straight ray in M87 matched none of that. It was smoother across colors than starlight has any business being, and it did not dim with distance from the galaxy's core the way starlight dims. Something was producing light by a mechanism with nothing to do with fusion. The mechanism came from a different branch of physics entirely, one built around charged particles and magnetic fields rather than stars. An electron forced to travel a curved path instead of a straight one radiates energy. This is not a subtle effect. Accelerating a charge in any direction forces it to shed energy as light. A particle moving in a straight line at constant speed radiates nothing. A particle being bent, even slightly, radiates continuously. Push that same principle to an extreme. Take an electron moving at a large fraction of the speed of light and force it into a tight spiral around a magnetic field line rather than a gentle curve. What comes off is not the soft glow of a star. It has a specific, identifiable signature called synchrotron radiation, first measured in particle accelerators on Earth years before anyone thought to look for it in space. The straight ray in M87 was built from exactly that mechanism. Electrons moving near light speed, spiraling around magnetic field lines stretched in a single direction, radiating as they went. A wire carrying ordinary household current does not glow visibly because the electrons inside it move slowly and follow no particular curve. Speed that same current up toward a meaningful fraction of light speed and force it along a twisting field rather than a straight copper path, and the electrons begin radiating at every wavelength in a beam pointed roughly along the direction they curl around. That is the process Curtis photographed in 1918 without the physics to name it. Electrons doing what accelerated charges always do, at a scale and speed no laboratory on Earth has ever reproduced. The distance involved changes how that mechanism should be weighed. M87, sits roughly 55 million light-years from where you are right now. Driving that distance at highway speed, near 100 kilometers an hour, would take something like 60 billion years, more than 4 times the current age of the universe. The light needed to see this ray directly left its source 55 million years ago, long before anything resembling a human being existed to look up and wonder about it. The ray is not a fossil, some finished event whose light is only now arriving. Whatever produces it is still producing it, at a distance so large that news of it takes tens of millions of years to reach anyone capable of noticing. The strange part is not that the ray exists. Physics allows accelerated charges to glow under exactly these conditions. The strange part is the discipline of it. A chaotic astrophysical process does not usually organize itself into a straight line stretching thousands of light years. Chaos scatters. It does not draw a ruler across a galaxy. Something at the heart of M87 was not merely energetic. It was organized, in a way ordinary stellar physics never predicts. There is a particular kind of quiet in realizing that a photograph from 1918 already contained the answer, decades before anyone had the framework to read it. Astronomers looked at the same plate, described the same straight line, and moved to other questions, not from carelessness, but because the tool needed to ask why it was straight had not been built. The evidence sat there the entire time, patient, unmoving, 55 million years old before it ever touched a photographic plate. Radio astronomy is what eventually forced the ray back into attention, decades later, picking up a separate signal from the same location, loud enough and structured enough that no one could file it away as an oddity a second time. The straight ray Curtis photographed and the radio source found later were 2 views of the same object, seen through 2 different windows onto the electromagnetic spectrum. Connecting those 2 observations opened a question. A straight ray alone could never raise on its own. If electrons were being organized into a beam this disciplined, something at the center of the galaxy had to be doing the organizing, continuously, for longer than any single observation could confirm. What could hold a beam of electrons together in a straight line across thousands of light years without it dissolving into the same disorder every other astrophysical process seems to obey? Something at the center of M87 was organizing electrons into a straight beam thousands of light years long, and organization on that scale needs a mechanism, not just a source of energy. Energy alone does not produce order. A star radiates enormous energy in every direction at once, and the result is a sphere, not a line. So whatever was happening inside M87 had to be doing 2 things simultaneously: accelerating particles to extreme speed and forcing them to travel in one direction rather than scattering outward the way energy normally does. Let's start with the acceleration itself. You already know that a spinning object holds energy in its motion, the same way a flywheel does, or the same way a top keeps standing upright as long as it keeps turning. Now imagine an object so massive and so compact that its own gravity has crushed it past any surface, past any solid boundary, into something general relativity calls a space-time curvature so extreme that nothing, not even light, can climb back out past a certain radius. That object still spins, and because it spins, it carries angular momentum, the same physical quantity that keeps a bicycle wheel resisting a push to tip over. A rotating black hole drags the fabric of space-time around with it, a real, measured effect called frame dragging, confirmed even around our own planet, using satellites sensitive enough to detect Earth's much gentler version of the same distortion. Near a black hole spinning near the theoretical limit, that dragging becomes ferocious. Magnetic field lines threading through the region around the black hole get caught in that dragging motion and twisted into a tight, rotating spiral, the way a stick dragged through wet cement leaves a spiral groove if you keep turning it in one place. The comparison is not decoration. The physics works almost the same way. A twisted magnetic field stores energy. The same way twisting a rubber band stores energy in the twist itself, not in anything moving through it. And just as a tightly wound rubber band releases stored energy along the axis you twisted it around, a magnetic field wound tight by a spinning black hole releases energy along that same rotational axis. This is the mechanism astrophysicists call the Blandford-Znaiec process, named after the two physicists who worked out the mathematics in the late 1970s. It lets a black hole extract energy directly from its own spin, without needing any matter to fall in and get consumed. The energy comes from rotation itself, siphoned off through the twisted magnetic field like current drawn off a generator. This solves something that should have bothered you back in the first act. A galaxy is full of stars and gas moving in every conceivable direction, and any process powered simply by matter falling into a black hole would inherit some of that randomness, spraying energy outward unevenly, not in a single disciplined line. But rotation has an axis. A spinning object has exactly one preferred direction built into it, the line running through its poles. Whatever process draws energy from that spin inherits the same preferred direction, not by choice, but by geometry. The beam has to run along the rotational axis, because that is the only direction the physics allows it to run. We are now in a position to ask a harder question. If the energy comes from the axis of rotation, and the axis of rotation of the black hole in M87 has held roughly steady for the entire time astronomers have observed it, then the beam we see today should be pointing in nearly the same direction it pointed decades ago, and likely centuries before that. That stability is worth taking seriously, because nothing else in a chaotic galactic environment stays that consistent. Stars wobble. Gas clouds get disrupted by passing stars and supernova shocks. The rotational axis of a 6.5 billion solar mass object, however, behaves like a gyroscope large enough that ordinary disturbances simply cannot budge it. You can feel a small version of that stability yourself if you have ever spun a bicycle wheel by hand and tried to tip it sideways while it kept spinning. The wheel resists the tip, pushing back against your hand in a direction that feels almost unrelated to the direction you pushed. That resistance is angular momentum, defending its axis, and it scales up enormously with mass and rotation speed. A black hole billions of times heavier than the Sun, spinning near the maximum rate general relativity allows, holds its axis with a stability no small object could ever match. So we now understand where the beam gets its energy and why it holds a single direction instead of scattering. What remains is why it looks, from Earth, disciplined enough to resemble a drawn line rather than a hazy, spreading glow, the way you'd expect from a flashlight beam spreading wider the farther its light travels. Part of the answer is that the magnetic field itself acts like a channel, the way a fire hose nozzle narrows a wide stream of water into a tight, coherent jet, instead of letting it spray outward the moment it leaves the hose. The twisted field lines confine the outgoing particles the same way that nozzle confines water, collimating them into a narrow column rather than letting them disperse in every direction the instant they are released. Confinement by magnetic pressure, not the pressure of a physical nozzle, but the same underlying principle. Energy contained within a boundary travels farther in one direction than energy released without any boundary at all. There is still a piece we have not accounted for. Even a well-confined beam of particles should slowly lose its collimation over a distance of thousands of light-years, the way even a tight fire hose stream eventually breaks into droplets given enough distance. The fact that the M87 jet stays this coherent across such enormous distances tells us the confining magnetic field itself must extend and remain organized across most of that length, not just near the black hole. Whatever is holding this beam together is doing so continuously along its entire path, not just at the moment of launch. That detail changes how you should think about the object we are describing. This is not an explosion that happened once and is still traveling outward from that single event, the way debris travels outward from a firework after it detonates. It behaves more like a continuously operating machine, one that has been feeding energy into the same magnetic channel for as long as the black hole has been spinning at this rate, likely for millions of years, possibly far longer. The beam is not a memory of something that happened. It is something actively happening right now, 55 million years ago from our perspective, but happening nonetheless, continuously, the entire time. We now know the fuel source, the direction, and the confinement. What we have not yet asked is what happens to particles caught inside that confinement once they are pushed close enough to the speed of light that ordinary intuition about speed and distance stops applying cleanly. Push a particle close enough to the speed of light, and distance itself starts behaving differently than intuition expects. Not because space changes, because the relationship between how far something travels and how long that travel takes stops matching anything you have ever experienced firsthand, at any speed you have ever moved it yourself. Here is the scale we are actually talking about. The jet coming out of M87 stretches somewhere between 3,000 and 12,000 light-years, depending on which wavelength you use to measure its visible extent. 12,000 light-years is not a number your intuition has anywhere to file, so put it next to something you already carry a feel for. The Milky Way, the galaxy containing Earth, spans roughly 100,000 light-years across its full disk. The jet from M87, on its own, without counting the galaxy that produced it, reaches somewhere close to 1/8 the width of an entire separate galaxy. A beam, not a galaxy. A single organized stream of particles launched from one point, reaching a fraction of the width of the Milky Way before it even begins to lose coherence. You need another anchor to feel that properly. Light itself, moving at roughly 300,000 kilometers every second, the fastest anything in this universe is permitted to move, takes 12,000 years just to cross the length of this jet. Human civilization, agriculture, cities, writing, all of it fits inside roughly the last 10,000 years. Light would still be crossing this jet, top to bottom, for longer than every human civilization that has ever existed has existed. And this is not a distance light crossed once, long ago. This is the length of something that exists right now, continuously, at every point along its structure. We are used to thinking of speed as something that shrinks distance. Drive fast enough, and a long trip becomes short. At the speed this jet moves, though, that relationship starts to break in an unexpected direction, and this is worth working through carefully, because it sets up something the next several acts depend on. Consider a commercial jet, cruising near 900 kilometers an hour, a speed you have probably experienced directly, sitting in a window seat. Cover the length of this cosmic jet at that speed, and the trip would take roughly 8 trillion years. The universe itself is about 14 billion years old. 8 trillion years is nearly 600 times the entire age of the universe, spent covering a distance that light itself needs 12,000 years to cross. That comparison should do something specific for you. It should make the speed of light feel less like an upper limit and more like a kind of local convenience, one so far beyond ordinary experience that ordinary experience gives you nothing useful to measure it against. And the particles inside this jet are not crawling toward that limit. Estimates place them at somewhere close to 99% of light speed, sustained continuously, not as a burst, not as a peak reached briefly and lost, but as an ongoing condition of the material inside the beam. At speeds this close to light, time itself, as measured by a clock traveling with the particle, runs slower relative to a clock sitting still and watching from outside. This is not speculation. It is measured routinely in particle accelerators on Earth, in muons produced by cosmic rays, in every GPS satellite, correcting for exactly this effect every single day to keep your phone's location accurate. A particle moving at 99% of light speed experiences time passing at roughly 1/7 the rate you would experience it, standing still. 7 years pass for you. 1 year passes for the particle. Now put those two things together, the distance and the time dilation, and something strange falls out of the mathematics rather than being added in for effect. From the particle's own perspective, riding along inside that beam, the 12,000 light-year length of this jet does not read as 12,000 light-years at all. Because the particle is moving so close to light speed, the distance it experiences contracts dramatically, a real effect called length contraction, the same physics responsible for the time dilation, just viewed from a different angle. From outside, we see 12,000 years of light travel time. From inside, riding with the particle, the crossing might take a span closer to a few years. Same journey, same physical event. Two entirely different durations, both correct, both measured accurately, neither one wrong. You do not need relativity to feel a small taste of this asymmetry yourself. Sit on a long flight and watch the in-flight map crawl across an ocean that takes hours to cross by your clock, while someone on the ground below experiences those same hours passing at what feels like the same rate you do, because neither of you is moving anywhere near fast enough for the effect to register. The particles inside this jet are moving fast enough that the effect stops being negligible and becomes the dominant fact of their experience. Time and distance are not fixed backdrops here. They are quantities that shift depending on how fast you happen to be moving relative to what you are measuring. We are not watching a single burst of matter that left the black hole once and has been coasting outward ever since. We are watching a structure that is, at every moment, actively fed, actively organized, with individual particles inside it experiencing a version of time so compressed relative to ours that what looks, from Earth, like a static, unchanging beam is, from the perspective of the material inside it, an active, ongoing journey lasting a comparatively short span. That gap between how long the jet appears to us and how briefly it registers to the particles inside it becomes important later, because it sets up something even stranger. If distance and duration already behave this differently depending on your reference point, at 99% of light speed, what happens to something moving even a fraction faster, angled just slightly toward the direction we happen to be looking from? Something inside this jet, according to the raw numbers coming off Chandra in 2026, appears to be moving 5 times faster than light itself is permitted to move. Not an error in the telescope. Not a miscalibration waiting to be corrected in a later paper. The measurement is real, repeated, and stable across observation windows. What it means is a different question entirely. Let's be precise about what 5 times the speed of light is actually describing. Nothing with mass has ever been clocked exceeding light speed, anywhere, under any condition physics has tested. Special relativity forbids it categorically, not as a rule of thumb, but as a structural feature of how space and time relate to each other. So the particles inside this jet are not breaking that limit. Something else is happening. Something in how we are measuring the motion rather than in the motion itself. Here is the setup. A blob of hot plasma inside the jet is moving toward us at roughly 99% of light speed, but not moving directly at us. It travels at a small angle relative to our line of sight, close enough to point it at Earth that the effect we are about to describe becomes extreme, but not so close that the geometry stops working. Picture the blob emitting a pulse of light at one moment, then continuing to move, and emitting a second pulse of light a short time later. Because the blob has moved closer to us between those two emissions, the second pulse has less distance to travel to reach our telescopes than the first pulse did. It is not moving faster. Its light simply has a shorter trip. Now stack that shortened trip against how far the blob has actually traveled sideways across our field of view during that same interval, and you get an apparent speed that has nothing to do with how fast the blob is really moving through space. The blob covers a real physical distance, sideways, at just under light speed. But because its light keeps arriving with less and less delay as it approaches us, the interval between when we receive the first pulse and when we receive the second pulse gets compressed far below the actual time elapsed for the blob to travel that distance. Divide a real large distance by a falsely compressed, tiny time interval, and the speed you calculate can come out several times the speed of light, even though nothing ever moved that fast. You can feel a distant cousin of this effect yourself, on the ground, on Earth. Stand near train tracks as a fast train approaches while sounding its horn, and the pitch you hear is higher than the pitch someone standing beside the train hears, because each successive sound wave has less distance to travel to reach you than the wave before it, compressing the wave arrivals and raising the apparent frequency. That is the Doppler effect, and it works on sound the same basic way superluminal motion works on light, through the geometry of a moving source, shortening the distance its signal has to cover. The astrophysical version simply pushes the source close enough to light speed and angled close enough to your line of sight that the compression becomes extreme rather than subtle. This phenomenon has a name among astronomers who study it, superluminal motion, and it was first proposed as an explanation, rather than observed directly, in the 1960s, years before instruments existed sensitive enough to actually measure it in distant radio sources. The physicist Martin Rees worked out the geometry mathematically well before the observational technology caught up to confirm it. That gap between prediction and confirmation is worth noticing on its own. Someone did the trigonometry on a phenomenon nobody had yet seen, and reality later arrived to match the math. We now have the mechanism. What determines how extreme the illusion becomes, in any individual case, is a specific and answerable question, not a fixed constant. Two variables control it entirely: how close to the actual speed of light the material is moving, and how small the angle is between its direction of travel and our line of sight. Push either variable further toward its extreme, and the apparent speed you calculate climbs. Push both at once, near light speed and a very shallow angle, and the apparent speed can reach many multiples of the true light speed limit, purely as an artifact of geometry. This means the 5 times measurement coming out of the M87 jet is not an arbitrary number. It is telling us something specific and useful about the angle at which we happen to be viewing this structure, information we could not have gotten any other way. We are not simply lucky bystanders watching a random cosmic event. The very fact that we perceive superluminal motion this pronounced tells us the jet is angled unusually close to our direct line of sight, closer than most jets we observe in other galaxies, most of which show far weaker apparent superluminal effects, or none at all. The organization, the discipline, the straight-line coherence of that beam of electrons, all of it is real, independent of any illusion. But the specific numbers describing how fast individual features appear to move within it are, in a strict sense, an artifact of our vantage point rather than a direct measurement of physical speed. Two separate observers, standing at 2 different angles relative to this same jet, would calculate 2 different apparent velocities for the exact same physical event, and both calculations would be internally correct, given their respective positions. That is a strange thing to hold steady in your mind. The same object, the same particles, the same true velocity, producing entirely different numbers depending on where the observer happens to be standing. Not because the universe is inconsistent, because velocity, unlike mass or charge, is not a property that exists independent of a frame of reference. It only exists relative to something else doing the measuring. We have untangled why the numbers lie without the physics lying. What we have not yet asked is what happens on the other side of this structure, on the far side of the black hole, where a second beam should exist by every symmetry argument physics offers, and where the same relativistic effects that inflate apparent speed on this side should do something very different to whatever is moving away from us instead of toward us. The true velocity hiding underneath that illusion is something we can actually pin down, and pinning it down is worth doing carefully because the number changes what you should feel about everything in the last act. Astronomers estimate the material inside this jet moves at somewhere close to 99% of light speed, not as an average smeared across slower and faster particles, but as a sustained condition of the fastest, brightest knots we can track individually. Here is the piece that makes the illusion possible in the first place, and it has nothing to do with speed alone. The angle between the jet's direction of travel and our line of sight from Earth sits at somewhere close to 14 to 20 degrees, depending on which study and which segment of the jet you are measuring. That is a narrow angle. Point your arm nearly straight out in front of you, then tilt it down by about the width your thumb covers at arm's length, and you have roughly the geometry we are talking about. Why does that narrow angle matter so much? Go back to the mechanism from the last act, the shrinking light travel time trick that inflated apparent speed past the true light speed limit. That trick depends entirely on how directly the moving object is aimed at you. Aim it straight at your face, and the effect becomes as extreme as physics allows. Aim it 90 degrees away, moving purely sideways across your field of view, and the effect vanishes completely, because sideways motion does not shorten the light's travel distance at all. We can be specific about this relationship, rather than leaving it vague, because the mathematics behind it is not complicated once you see the shape of it. The apparent speed you calculate depends on two things multiplied against each other in a particular way. The true speed of the material, expressed as a fraction of light speed, and the sine of the viewing angle sitting in the denominator of the equation. Push the angle small enough, and that denominator shrinks towards zero, which means the calculated apparent speed can grow arbitrarily large, even without the true speed changing at all. There is a specific angle where this effect peaks rather than climbing forever as the angle shrinks, and that detail matters more than it might first seem. For material moving at 99% of light speed, the apparent speed is maximized at a viewing angle of roughly 8 degrees, not 0. Below that angle, the apparent speed actually starts decreasing again because the light from the source starts arriving so compressed in time that a different relativistic effect, extreme dimming from the material moving almost directly away from an observer positioned behind it, begins to dominate instead. M87's jet sits close enough to that peak angle that the apparent speed we observe, somewhere around 5 times light speed, falls almost exactly where the mathematics predicts it should, for material moving at 99% of true light speed and viewed from 14 to 20 degrees off axis. That agreement is not a coincidence dressed up to sound impressive. It is a genuine cross-check, two independently measured quantities, the apparent speed and the estimated viewing angle, landing inside the same equation and confirming each other. Think about what this means for anyone trying to study a jet like this one from any other galaxy. Most jets in the universe are not aimed anywhere close to Earth. They point off at wide angles, sideways or nearly so, relative to our line of sight, and from those angles, none of this superluminal inflation happens at all. We would simply see the true speed, undistorted, unremarkable by comparison. M87 happens to be one of the rare cases where the geometry lines up close to ideal for us specifically. Not because the universe favored Earth in any way, because among the thousands of galaxies with active jets, some small fraction will always happen to point close enough to any given observer's line of sight for this effect to appear, purely by the odds of how many jets exist and how many possible angles a jet can be oriented at. You can feel a related idea with something far more mundane than a black hole. Watch a firework explode directly overhead, and the falling sparks appear to radiate outward and downward in every direction at similar speeds, roughly matching what you'd expect from the explosion. Watch the same kind of firework explode from far off to the side, nearly at the horizon, and the sparks moving directly toward you seem to hang in place far longer than the sparks moving away, purely because of how their light reaches your eyes at different rates depending on direction. Your brain is doing a rough, everyday version of the same geometric trick the M87 measurement depends on, just without the relativistic extremes involved. Return to the black hole itself, and a new question opens that a firework cannot help you answer. If the angle we happen to be viewing this jet from is this specific, this close to the value that maximizes the illusion, what does the jet actually look like from directions we are not standing in? Symmetry gives us an answer before any telescope does. A rotating black hole extracting energy along its spin axis has no physical reason to produce a beam in only one direction. The same magnetic field twisting described earlier operates on both poles of the rotation axis simultaneously, which means a second beam aimed the opposite direction should exist as a basic consequence of the geometry, not as a hopeful guess. The deeper truth is that the astonishing speed we measure is as much a trick of perspective as it is a property of the jet itself. Change the observer's position, and the numbers change with it, even though the underlying event remains exactly the same. That insight transforms the entire picture around the black hole. A jet aimed toward us should always have a twin aimed away. But the same relativistic effects that make one appear extraordinary should hide the other so effectively that it becomes one of the most elusive features in the entire system. Everything we have unpacked so far about this jet depends on one fact we have not looked at directly. What we see is not what is happening. It is what happened, delayed by exactly however long the light took to reach us. That gap between event and perception sounds abstract when you're talking about 55 million years. It is not abstract at all when you look at how your own senses work, right now, in the room you are lying in. Your eyes are not reporting the present moment to you. They never have been, not once, in your entire life. Light bounces off whatever you are looking at, travels to your retina, gets converted into an electrical signal, and that signal takes a measurable amount of time to reach your brain and become a conscious image. Even across a room, across a few meters, you are looking at a version of that room that is already slightly in the past by the time you register it. The delay across a room is too small for you to notice. A few nanoseconds for the light, a few tens of milliseconds for your nervous system to process it. But the mechanism is identical to the one separating you from this jet by 55 million years. Only the distance changes. The principle, light needs time to travel, and your perception waits for that travel to finish, is exactly the same at both scales. You have felt a version of this delay stretched large enough to notice, even if you never called it by this name. Stand far enough from someone chopping wood, watching them swing an axe, and you will see the axe strike the log a moment before you hear the sound of the impact. Light from the swing reaches you almost instantly. Sound from the impact takes longer because sound moves through air at roughly 340 meters a second, dramatically slower than light. The bigger the distance between you and the woodpile, the bigger that gap between seeing and hearing grows. Lightning and thunder work the same way, at a scale most people have actually clocked without realizing they were doing physics. You see the flash essentially the instant it happens, because light crosses those few kilometers of air in a fraction of a second. The thunder, generated by the same event, takes roughly 3 seconds to cross each kilometer of distance to reach your ears. Count the seconds between flash and sound, divide by 3, and you have the distance in kilometers to the strike. People have used this trick for centuries without needing to understand the physics behind it. They just noticed that a bigger gap meant a farther storm. What that trick actually reveals, once you look at it carefully, is something larger than storm distance. It reveals that different signals carrying information about the exact same event can arrive at wildly different times, purely because they travel at different speeds through the same space. The flash and the thunder come from one strike, one single moment in time. But by the time both signals reach you, they have been pulled apart, stretched across seconds, simply because light and sound do not travel at the same speed through air. Every photon leaving the base of that jet and every photon leaving its farthest visible tip both travel at the same speed, light speed, no exceptions. But they do not leave at the same distance from Earth. The near end of the jet is measurably closer to us than the far end, by thousands of light years. Which means the light reaching your ears, or in this case your eyes, from different parts of the same structure, left those different points at different times, arriving here only now, bundled together into a single image that looks momentary but is, underneath, a patchwork of light with ages spanning thousands of years within the same photograph. There is no version of this jet, none, where an observer anywhere sees it as it exists right now, in the present moment defined at the source. Even a hypothetical observer sitting just outside M87 itself would face the identical problem, just compressed to a smaller scale, because light still needs time to cross even a few thousand light years. Nobody, anywhere in this universe, gets to see this structure without some version of this delay built in. Not because our instruments are limited, because the delay is not a limitation of measurement. It is a basic feature of how information moves through space at all. This matters for a reason that goes beyond appreciating a neat parallel between lightning and cosmic jets. It tells us something about the confidence we should carry into every measurement we have discussed so far, and every measurement still ahead. When we say the jet stretches 12,000 light years, we are describing light that left different points along its length at different times, now arriving together. When we say material moves at 99% of light speed, we are inferring that from how features shift position across multiple exposures, themselves each already delayed by the same travel time problem. Every number in this story has passed through a filter of delay before it ever reached a human eye or a scientific instrument, and understanding that filter is what lets scientists trust the numbers rather than be fooled by them. Once astronomers understood exactly how light travel delay distorts what an observer sees, from any angle, at any distance, they could work backward from the distortion to recover the truth underneath it. The superluminal illusion is a direct product of this same delay mechanism, just pushed to its geometric extreme by an object moving close enough to light speed and angled close enough to our line of sight. Understanding the mechanism does not eliminate the illusion. It lets you see through it. That distinction between an illusion you cannot detect and an illusion you can account for mathematically is the entire difference between being fooled by this jet and actually understanding it. If everything we have measured about the near side of this structure has passed through exactly this kind of delay and distortion, what happens to the light traveling toward us from the far side, the side moving away rather than toward, the side that symmetry insists must exist, but that neither Curtis in 1918 nor most instruments since have ever managed to see? A black hole extracting energy from its own spin does not have a reason to favor one pole over the other. The magnetic field twisting around the rotation axis wraps both ends of that axis at once, which means the same mechanism behind the beam we've been discussing should be generating a second beam, right now, pointed in the opposite direction. You have every reason to expect astronomers found that second beam decades ago. They did not. For most of the 20th century, and well into the 21st, the counterjet of M87 was functionally invisible, detected only in scattered, faint hints that most instruments could not confirm with confidence. A structure required by the same physics producing the 12,000 light-year beam we already understand in detail, sitting there the entire time, refusing to show itself clearly. Here is the mechanism responsible, just pointed in the opposite direction this time. The visible jet appears bright partly because it moves close to light speed toward us, and that motion toward an observer does something specific to the light it emits. Photons emitted by a source moving toward you arrive compressed in both time and energy, an effect called relativistic beaming, which concentrates the emitted light into a narrower cone and boosts its apparent brightness dramatically beyond what the source would show if it were standing still. Now flip that same physics around. A source moving away from you at close to light speed does the opposite. Its light gets stretched rather than compressed, spread across a wider cone instead of narrowed into a beam pointed at your eyes, and its apparent brightness drops by the same enormous factor that boosted the approaching jet's brightness. This is not a small correction. For material moving at 99% of light speed, the difference in apparent brightness between the approaching and receding sides can reach a factor of hundreds, sometimes closer to 1,000. Picture two flashlights, identical, same bulb, same battery, held by two people walking away from each other at a brisk pace, one walking toward you, one walking away. If both flashlights were ordinary, you would see both beams at roughly the same brightness, adjusted only for the ordinary fall-off of light with distance. But if those two people were somehow walking away from each other at 99% of light speed, and only then, the flashlight moving toward you would look almost blinding, while the flashlight moving away would fade towards something you might miss entirely against the dark sky behind it. Nothing about the bulbs changed. The motion itself reshaped how their light reaches you. That is the entire explanation for why the counterjet resisted detection for so long. It is not fainter because it carries less energy or contains less matter. It is fainter because relativistic beaming punishes anything moving away from an observer with almost the same severity it rewards anything moving toward one. The physics producing an easily visible jet on one side guarantees an almost invisible jet on the other, as a direct mathematical consequence, not as some separate coincidence needing its own explanation. We should sit with what this means for the history of studying M87. Every astronomer who looked at this galaxy for most of the last century was looking at exactly half of a symmetric structure and had no way of knowing, from the image alone, that the other half existed at all. The absence looked like nothing rather than like a signal being actively suppressed by relativity. You cannot distinguish nothing is there from something is there, but hidden by physics using an image alone. You need a specific kind of measurement designed to catch precisely this kind of hidden signal. Radio astronomers eventually found faint traces, fragments consistent with a counterjet, scattered through observations across several decades, none of them decisive on their own. Each individual detection could be explained away as instrumental noise or an unrelated background source. It took accumulating evidence across many independent observations, using increasingly sensitive radio interferometry, before the case for a genuine counterjet became difficult to dismiss. Then, near the end of 2025, James Webb's infrared instruments captured something no earlier generation of telescope had managed. A faint but genuine infrared counterpart to the counterjet, extending roughly 6,000 light-years from the black hole, on the side we had spent a century failing to confirm. Think about what had to happen for that detection to succeed where a century of effort had not. Infrared light sits at a longer wavelength than visible light, and longer wavelengths suffer less from the specific kind of relativistic beaming suppression affecting shorter wavelengths on a receding source. It was not a matter of pointing a bigger telescope at the same problem. It required looking at a different part of the electromagnetic spectrum entirely, one where the physics penalizing the counterjet's visibility happened to be less severe. There is something worth noticing in how long this took, set against how simple the underlying symmetry argument always was. Nobody needed a new theory to predict the counterjet should exist. The prediction followed directly from physics established decades earlier. What took a century was not the idea. It was building an instrument capable of catching a signal that the same physics producing our best-known jet was actively working to hide from every telescope not specifically suited to the task. Confidence in a mechanism and confidence in an observation are not the same kind of confidence, and mistaking one for the other is exactly how good physics gets treated as settled before it has actually been checked. We now have both halves of this structure confirmed, one blindingly bright by an accident of geometry, one faint enough to have escaped detection for most of the century we have spent studying its twin. Both halves trace back to the same source, the same spinning black hole, the same twisted magnetic field, launched at the same moment in the deep history of this galaxy. Confirming that the counterjet exists closes one gap in this picture, but it opens a harder one immediately behind it. If James Webb managed to catch this structure only by reaching for a wavelength most of a century's worth of instruments never used for this purpose, what else about this jet, on either side, might still be sitting in exactly that kind of blind spot, visible only to an instrument nobody has pointed at it yet in quite the right way? We already know the counterjet exists. What we have not looked at closely is how James Webb actually managed to catch it, and that detail matters more than it might seem at first. Confirming a prediction and capturing it directly are two different achievements, and the gap between them tells us something about the limits of every instrument that came before this one. Start with the wavelength itself. Visible light and infrared light are both electromagnetic radiation, but they carry information differently depending on what they pass through and what emitted them. The counterjet's light had spent 55 million years crossing space, and along the way, some of the shorter wavelengths that make up visible light get absorbed or scattered by interstellar dust far more easily than longer infrared wavelengths do. A faint signal already weakened by relativistic dimming, then further weakened by scattering across intervening dust, can drop below what a visible light telescope can distinguish from background noise. Infrared light survives that same journey more intact. Think of it the way sound behaves passing through a heavy fog. A high, thin whistle gets swallowed almost immediately, scattered apart by water droplets suspended in the air. A low, deep foghorn carries much farther through the exact same fog because longer sound waves interact with small droplets far less than short ones do. Light behaves by a related principle when it passes through interstellar dust, longer wavelengths slipping through relatively undisturbed, while shorter wavelengths get absorbed and redirected. James Webb was built specifically to work in that longer, quieter part of the spectrum, and that design choice, made years before anyone pointed it at M87, is what let it catch a signal that had been sitting there the entire time, simply arriving in a form most instruments were never built to hear. The observation itself came together near the end of 2025, using Webb's near-infrared and mid-infrared instruments in combination, comparing images taken months apart to separate genuine structure from noise. What emerged was a faint plume extending roughly 6,000 light-years from the black hole, on the exact side symmetry had insisted must contain a counterjet aligned with the axis already established by the visible jet on the opposite side. The counterjet did not appear as a simple, faint mirror image of the bright jet, uniform and predictable. It showed internal structure, brighter knots, and fainter stretches, distributed unevenly along its length, in a pattern that did not simply track the pattern already known from the bright side. If both jets were launched by the same symmetric mechanism at the same moment, you might expect their internal structure to roughly mirror each other, knot for knot, stretch for stretch. The counterjet's internal pattern did not mirror the bright jet's pattern cleanly. That mismatch raises a specific, testable question rather than a vague mystery. Either the two jets are not being fed with identical timing, meaning whatever process launches material into each direction fluctuates independently rather than as a single synchronized event, or the material in each jet is interacting differently with its surrounding environment as it travels outward, shaped by gas and magnetic turbulence that differs slightly on each side of the black hole. Both explanations remain live. Neither has been ruled out by the current data. You can hold that kind of open question without discomfort, because science routinely lives inside exactly this kind of gap. A measurement can be completely real, entirely trustworthy, and still leave the deeper mechanism behind it only partially explained. The counterjet's existence is settled. Its internal structure raises a new, specific question that current instruments have not yet resolved. A bright feature near the base of the visible jet, catalogued decades earlier under the name HST-1, located roughly 60 light-years from the black hole, had long been treated as a single, compact knot of emission. Webb's higher-resolution imaging resolved that single feature into two distinct, separate structures, sitting close together but not merged into one. This matters beyond simple bookkeeping about how many bright spots exist along the jet. A single knot suggests one localized disturbance, one event in the flow of material producing one bright feature. Two adjacent, separate knots suggest something closer to a recurring or ongoing process, producing distinct disturbances close together rather than one isolated event. The jet, near its base, may be more actively, more continuously turbulent than the earlier, lower-resolution images ever allowed anyone to tell. Every increase in resolving power we have applied to this object, across a century of instruments, has revealed structure the previous generation of images simply could not show, not because that structure appeared recently, but because no earlier instrument had the resolution to separate it from a single blur. That pattern of structure hiding inside apparent simplicity until a better instrument arrives deserves to be taken seriously as a general principle here, not just a footnote about one bright spot near the base of one jet. Every time astronomers have built a more sensitive telescope and pointed it at M87, the object has not simplified. It has gotten more intricate, not less, revealing substructures inside what previously looked like single, uniform features, which raises an uncomfortable question about confidence. If a century of steadily improving instruments has consistently revealed more internal structure than the previous generation could detect, what confidence should we actually hold in the picture we have built so far, using instruments that are, by definition, the best available today but almost certainly not the best that will ever exist? We now have both jets confirmed, one bright by geometric accident, one faint by the same accident working in reverse, and internal structure inside both that keeps resolving into more detail every time the resolution improves. What remains, after both jets have been found and partially mapped, is the one location neither jet's discovery has actually pinned down. The exact point, close to the black hole itself, where this entire structure begins. Both jets are confirmed now. One bright, one faint, both traced back to the same rotating black hole. What we have not actually pinned down is the one point that should be simplest to find, exactly where it begins. That should sound strange to you, and it should sound strange precisely because of how much we have already measured. We know the jet's length, its speed, its angle, its power source, its twin on the far side. We do not know, with any real precision, the exact distance from the event horizon where this structure first becomes a coherent beam rather than a chaotic swirl of infalling material. Here is why that gap exists. And it comes down to a limitation built into the geometry of observation itself, not a failure of effort. M87's black hole sits 55 million light-years away. Even the sharpest instrument humanity has ever pointed at it faces an unavoidable trade-off between how far away something is and how small a detail you can resolve at that distance. Resolving power depends on the size of your telescope's aperture relative to the wavelength of light you are observing, and at radio wavelengths, useful for tracing magnetic structure, the practical aperture needed to resolve something the size of the jet's actual launching region would require a dish larger than the Earth itself. Nobody builds a telescope the size of a planet. Instead, astronomers built something almost as strange. The Event Horizon Telescope links radio dishes scattered across multiple continents, from Hawaii to Chile to Spain, and combines their signals using a technique called very long baseline interferometry, treating widely separated dishes as if they were pieces of one enormous telescope, spanning nearly the diameter of Earth itself. Picture what that actually requires. Each dish records the radio signal arriving from M87 with an atomic clock precise enough to timestamp every wave crest to within a fraction of a billionth of a second. Later, computers combine the recordings from every site, correcting for the exact distance and timing differences between them, reconstructing an image as if one dish the size of the planet had captured it directly. This is not a metaphor for how the technique works. It is a literal description of the mathematics involved, one requiring atomic clock precision spread across 10,000 kilometers to succeed at all. Even with that extraordinary setup, resolving the exact region where the jet launches remains close to the theoretical edge of what is possible today. In January of 2026, new Event Horizon Telescope data offered the first genuine hint at the answer, placing the launching point at roughly 9% of a light-year from the black hole itself, a distance close to where theoretical models had predicted the magnetic field structure should first organize into a coherent, collimated beam. 9% of a light-year sounds small. Next to the 12,000 light-year length of the jet, we have spent this entire story examining. It is not small at all, measured against the black hole itself. 9% of a light-year comes out to roughly 550 astronomical units, where 1 astronomical unit is the average distance from Earth to the Sun. 550 times that distance would place you well beyond Pluto's orbit, out past the Kuiper Belt, deep into the region where the Sun's gravity barely holds anything at all. That is the scale at which this jet is still being organized. 550 times the distance from the Sun to Earth, and the beam has not yet finished collimating into the straight, coherent line Curtis photographed in 1918 without understanding what he was looking at. We should be honest about what first hint actually means here. The January 2026 data represents an early result, consistent with theoretical predictions, gathered from an observation technique still being refined and cross-checked against independent methods. Confidence in this specific number should sit lower than confidence in the jet's length or its approximate speed, both measured multiple independent ways across decades. Close to the black hole, the material producing observable radio emission sits in an environment thick with turbulent plasma, strong gravitational lensing distorting the paths light takes to escape, and magnetic fields so intense and so rapidly changing that separating the jet's true launching structure from the surrounding accretion chaos requires disentangling signals that overlap in both space and time. Every improvement in resolution reveals more of that overlap, not less. The same pattern we noticed with the HST-1 not splitting into 2 structures once Webb's resolution improved. Think about what that pattern implies for how you should hold everything else in this story. The exact launching point of this jet sits at the frontier where that pattern is actively happening right now, live, in data being analyzed as recently as this year. We are not looking at a settled answer. We are looking at the edge of what current technology can even attempt to measure. That edge is not a failure of the science. It is the honest boundary of it. The specific line where confirmed physics gives way to active research, where a century of measurement stops and the genuinely unresolved question begins. We have now followed this structure from a straight line on a photographic plate in 1918, through the mechanism powering it, the illusion distorting our view of it, the twin hiding on its far side, all the way down to the very edge of where human instruments can currently see. What remains is not a new fact about the jet itself. It is a question about the source generating all of it, the object whose mass and spin have to be large enough, stable enough, to keep feeding a beam this disciplined for longer than most stars in the visible universe have existed. We have followed this jet down to the very edge of where it begins, roughly 550 times the distance from the Sun to Earth, still assembling itself into the disciplined beam we have tracked since the first act. What we have not actually confirmed, this entire time, is where the energy driving all of it actually comes from. A black hole surrounded by infalling gas heats that gas to extreme temperatures as it spirals inward, and hot, compressed, magnetized gas can radiate enormous amounts of energy. Surely, you might think, that infalling material is what powers a beam this bright, this far-reaching, this old. Run the numbers, though, and that explanation runs into trouble almost immediately. The rate at which matter is falling into M87's black hole, measured through the X-ray and radio emission from its accretion disk, is remarkably modest for an object this massive. Estimates put it at a small fraction of a solar mass per year, some studies suggesting numbers as low as a few hundredths of a solar mass annually. That is not a large fuel supply for a beam, carrying the kind of power needed to stay collimated and visible across 12,000 light-years. Here is the specific mismatch that forced physicists to look elsewhere. The jet's total power output, estimated from its radio and X-ray luminosity, comes out to roughly 10 to the 42nd power watts, sustained continuously. Converting even a generous fraction of the infalling matter's mass into energy, using Einstein's mass-energy relationship, falls well short of supplying that continuously. Over the timescales, the jet has clearly been active. Something else has to be supplying the difference. That gap is exactly what the Blandford-Znajek mechanism, the one we worked through back in the second act, was built to close. A rotating black hole does not need matter falling in to have energy available. Rotation itself is a form of stored energy, the same physical quantity that keeps a spinning top upright and a thrown discus flying stable through the air. A black hole spinning near the theoretical maximum rate holds an enormous reservoir of that rotational energy, entirely separate from whatever matter happens to be falling toward it at any given moment. You have felt a small, safe version of this distinction yourself, even if you never thought about it this way. Pedal a bicycle up to speed, then stop pedaling. The bike keeps moving, coasting on stored momentum without any new energy input at all. Now compare that to constantly pushing a shopping cart, where the moment you stop pushing, the motion stops too, because nothing stored is carrying it forward on its own. A black hole's spin behaves like the coasting bicycle, not the shopping cart. The energy is already there, banked in the rotation, available to be drawn on without needing continuous fuel. The question that follows is mechanical rather than conceptual. How exactly does rotational energy, stored in the space-time around a black hole, get extracted and converted into a directed beam of particles moving at 99% of light speed? Magnetic field lines threading through the region just outside the event horizon get anchored partly by the surrounding accretion disk and partly dragged by the black hole's own rotation through the frame-dragging effect we described earlier. Where those field lines connect the spinning black hole to the slower rotating material farther out, they behave like a mechanical linkage between two objects spinning at different rates, one being forced to catch up to the other. Picture two gears of very different sizes connected by a drive belt, one spinning fast, one spinning slow, with the belt itself under constant tension trying to equalize the mismatch between them. The belt does not create energy out of nothing. It transfers energy from the faster gear to the slower one, doing mechanical work in the process. And that work has to come from somewhere, specifically from the rotational energy of the faster gear, which gradually slows as a result. The magnetic field lines around M87's black hole function as that belt, connecting the black hole's extreme rotation to the particles far outside it, transferring energy from the spin into the particles being flung outward along the field lines. Every joule pushed into the jet is a joule the black hole's spin gives up in exchange. This is a genuinely strange thing to hold steady in your mind. A black hole loses angular momentum, imperceptibly, continuously, every time it launches material outward along this jet. Over sufficiently long timescales, this process can measurably spin a black hole down, though for an object with the mass of M87's, that timescale stretches far beyond anything relevant to human history. If the jet were powered mainly by infalling matter, its power output should track fairly closely with how much matter is currently falling in, rising and falling together over time. Observations spanning multiple decades show the jet's power staying comparatively stable even as the accretion rate fluctuates, a pattern far more consistent with a steady rotational energy source than with a supply tied directly to variable infall. We should be careful, though, about overstating how cleanly this case is closed. Most researchers studying M87 favor the Blandford-Znayak mechanism as the dominant contributor, supported by the power mismatch, the stability argument, and independent estimates of the black hole's spin from Event Horizon Telescope data. A smaller contribution from infalling matter almost certainly still plays some role, feeding the accretion disk that helps anchor the magnetic field in the first place, even if it is not the primary energy source itself. The two mechanisms are not strictly separate. The infalling matter and the spinning black hole work together, one providing the field's anchor, the other providing most of the actual power. We now understand where the energy comes from, and we understand the mechanical linkage carrying it outward. None of that yet tells us how massive this particular black hole actually is, and mass is exactly what determines how much rotational energy was available to begin with, how large a reservoir this specific object was given, and how long that reservoir could plausibly keep a beam like this one burning without running dry. We now understand the mechanism supplying this jet's energy. What we have not measured yet is the size of the reservoir that mechanism draws from, and that number changes everything about how long this beam could plausibly keep running. The black hole at the center of M87 has a mass of roughly 6.5 billion times the mass of the Sun. Numbers at this scale slide past you unless you give them somewhere to land, so put it next to something you already carry a working sense of. The black hole at the center of our own galaxy, Sagittarius A star, holds a mass of roughly 4 million suns. M87's black hole outweighs the one anchoring our entire galaxy by a factor of more than 1,600. Not 1,600% larger, 1,600 times as massive. Picture the difference this way. If Sagittarius A star were a single grain of sand resting in your palm, M87's black hole, at the same relative scale, would be a pile of sand weighing more than a car. Both are still, technically, supermassive black holes. The category itself spans a range wide enough that comparing them side by side stretches the meaning of putting them in the same category at all. The Blandford-Znayak mechanism draws power from rotational energy, and the amount of rotational energy available scales with mass. A more massive black hole, spinning at a comparable fraction of its theoretical maximum rate, holds proportionally more energy in its spin, simply because there is more of it turning. You can feel a rough version of this relationship with something far more modest than a black hole. Spin a small toy top and a large flywheel at the same rotational speed, and the flywheel holds dramatically more kinetic energy, not because it spins faster, but because it carries more mass moving through that same rotation. Mass and rotation together determine how much energy is actually banked in the spin, and M87's black hole banked an amount that dwarfs almost every other black hole discovered so far. This is not simply a matter of having a bigger fuel tank, though. Mass changes something more fundamental about how long a structure like this can remain stable, and stability turns out to be the real constraint governing whether a jet like this one can exist at all. A less massive black hole spinning near its maximum rate experiences its surrounding environment as comparatively chaotic. Gas clouds, passing stars, occasional smaller black holes merging in from nearby mergers. All of these disturbances exert torques capable of nudging a smaller object's rotational axis measurably over relatively short timescales. A black hole with the mass of M87 simply has too much rotational inertia for any of those ordinary disturbances to matter. The same physics keeping a spinning bicycle wheel resistant to a sideways push, scaled up by a factor large enough that the entire galaxy's ordinary turbulence barely registers against it. That stability is precisely what let this jet stay pointed in almost the same direction for as long as it has. If the axis wandered even slightly, drifting a few degrees over a few million years, the beam we have traced across 12,000 light-years would show a visible curve or kink where the direction shifted, rather than the straight line Curtis photographed in 1918 without understanding what he had captured. The line stays straight because the axis generating it has barely moved, and the axis has barely moved because the object anchoring it is too massive for the galaxy's ordinary disturbances to budge. Stars and gas clouds orbiting near the galactic center move under the black hole's gravitational pull, and their orbital speeds reveal the mass they are orbiting, the same basic principle letting astronomers weigh our own sun by watching how fast Earth orbits it. Multiple independent methods, gas dynamics, stellar orbits, and the Event Horizon Telescope's direct imaging of the shadow itself converge on the same range for M87's black hole mass, each using entirely different physics to arrive at compatible numbers. Three separate techniques, built on three separate sets of assumptions, would not be expected to land in the same range purely by chance if the underlying mass estimate were badly wrong. Here is a detail that complicates the picture slightly, and it is worth sitting with rather than smoothing over. The Event Horizon Telescope's imaging method and the stellar orbit method produced mass estimates that, in earlier analyses, sat in mild tension with each other, differing by a factor that mattered scientifically, even if it sounds small conversationally. Later refinements to both methods narrowed that gap considerably, but the fact that it existed at all is worth remembering. Even a measurement this well supported, converging across independent techniques, went through a period of real disagreement before settling into the range astronomers now treat with confidence. A black hole this massive holds enough rotational energy and enough resistance to disturbance to keep a beam collimated and pointed in nearly one direction for longer than the age of most stars visible in Earth's night sky. That raises a question this act has not yet touched. If the mass and the mechanism together explain why the jet stays stable, they say nothing yet about how long the jet has actually been running and whether the structure we see today looks anything like the structure that first switched on. The mass and stability we just established explain why this beam stays pointed in nearly one direction for so long. They say nothing about whether the beam itself has stayed the same while doing it. Most descriptions of this jet, including everything we have built across the last 11 acts, treat it as a fixed structure, a permanent line drawn across the galaxy once and left in place. Chandra's X-ray observations, repeated across multiple years, tell a different story, one that changes the entire feeling of the object we have spent this much time understanding. Chandra photographed this jet in 2012, again in 2017, again in 2023, and again in 2025. Line those four images up side by side, and the bright knots scattered along the jet's length are not sitting in the same places. Some have dimmed considerably. Others have brightened where nothing bright existed before. A few have shifted position outward, slowly, measurably, across the 13 years separating the first image from the most recent one. A structure with the discipline to stay straight for over a century, powered by a black hole too massive for ordinary disturbances to nudge its rotational axis, sounds like it should be frozen, permanent, essentially unchanging on any timescale a human being could witness directly. The Chandra time-lapse says otherwise. This jet is rearranging itself, visibly, on a timescale of years, not millions of years. Here is the mechanism responsible, and it does not contradict anything we established about the jet's overall stability. It simply operates at a different layer of the structure entirely. The electrons producing the synchrotron radiation we discussed back do not radiate forever at the same brightness. Every time an electron spirals around a magnetic field line and sheds energy as light, it loses a small amount of its own kinetic energy in the process. Radiate long enough, and the electron slows down, and a slower electron radiates at a different, generally lower frequency and lower intensity than a faster one. This process has a name, synchrotron cooling, and it happens on a timescale that depends specifically on how energetic the electron was to begin with and how strong the magnetic field around it is. The most energetic electrons, the ones producing the brightest, highest frequency light we can observe, burn through their energy fastest, cooling and dimming within years to decades. Less energetic electrons, producing dimmer, lower frequency light, cool far more slowly, over centuries or longer. Picture a bed of embers scattered across a campfire that has stopped receiving new logs. The brightest, hottest embers burn down fastest, fading within minutes, while the duller, cooler embers underneath can hold their glow for hours after the brightest ones have already gone dark. Both are cooling by the same basic process, losing stored energy as light and heat, but the brightest ones simply had further to fall and less patience for the trip. The knots along M87's jet behave the same way. At every wavelength we can observe, cooling and dimming at rates set by how energetic each individual patch of electrons happened to be when we first caught sight of it. If a knot is dimming rapidly across a few years, we can work backward from that cooling rate to estimate how energetic its electrons must have been to begin with, and that estimate, combined with the knot's known distance from the black hole, tells us roughly when that batch of material was launched. The jet's brightness pattern is not just decoration. It is a kind of fossil record, encoded in light, of when different pulses of material left the black hole's vicinity. If different knots along the jet were launched at noticeably different times, carrying different amounts of energy, then the black hole is not feeding this jet with the smooth, constant flow our earlier acts may have implied. It is feeding it in pulses, episodes of stronger and weaker energy release, layered on top of the steady rotational power we described in Acts 10 and 11. The jet's underlying direction stays locked by the black hole's enormous rotational stability. Its intensity, moment to moment, patch to patch, is anything but steady. You should sit with what this means, because it changes the picture we've been building of this object. The picture that has gradually emerged is one of extraordinary stability, a beam locked onto a single axis by a black hole too massive to be pushed off course. That picture remains true. What we had not yet accounted for is that stability in direction does not require stability in output. A river can follow the exact same channel for centuries while still varying, year to year, in how much water it actually carries. A river's channel is shaped by geology, bedrock, and slope, factors that change over geological timescales far longer than any single flood or drought. The water level inside that channel, though, responds to rainfall, snowmelt, and seasonal cycles operating on timescales of months and years, completely independent of how slowly the channel itself is carved. Two different processes, two different timescales, occupying the same physical structure without contradicting each other. M87's jet works the same way. Its direction is carved by the black hole's rotational axis, changing imperceptibly over cosmic timescales. Its brightness is carved by however much energy happens to be flowing through the magnetic channel at any given moment, changing measurably within a single human decade. 4 snapshots, however well separated in time, are still 4 snapshots. They confirm that meaningful change happens on a timescale of years to decades. They do not yet give astronomers a complete, continuous record of how that variability behaves over longer stretches, whether it follows any repeating pattern or whether it is closer to unpredictable turbulence. That distinction between confirmed change and understood pattern matters, and honesty requires keeping it visible rather than letting the imagery imply more certainty than the data currently supports. What this act leaves us with is not a settled fact folded neatly into everything that came before. It is a genuine complication, one that reshapes how confidently we should describe any single measurement of this jet as permanent. If the brightness pattern along this beam is still actively shifting within a human lifetime, then every earlier act in this story, however carefully measured, has been describing a version of this jet that existed only in the specific years those measurements were taken, not some final, unchanging truth about the object as a whole. How much of what feels certain in this story is actually a permanent feature of the physics involved, and how much is simply the version of events that happen to be true during the narrow window of decades human instruments have existed to observe it? Let's actually separate what we have measured from what we have modeled, act by act, and see how the balance holds up. Start with the straight line itself, the one Curtis photographed in 1918. That is direct observation, confirmed independently across more than a century of instruments, from photographic plates to radio dishes to Chandra's X-ray optics. Nobody needs a model to see it. It shows up in every wavelength anyone has pointed at that spot in the sky. The synchrotron mechanism producing that light sits on slightly less certain footing, though not by much. We understand synchrotron radiation extremely well, because physicists produce it deliberately, on purpose, inside particle accelerators here on Earth, and the spectrum it produces in a lab matches the spectrum coming from M87’s jet closely enough that this identification counts as settled physics, not speculation. The jet's length, its approximate speed, its viewing angle, these come from combining direct measurement with the mathematics of relativistic beaming. This is not guesswork. It is measurement filtered through a well-tested equation, the kind of equation that has been checked against other systems, other jets, other angles, and consistently holds up. The counterjet's existence, confirmed directly by James Webb, sits in the same category. Observed, not inferred from symmetry alone anymore, though symmetry predicted it decades before any telescope caught it. Now here is where the confidence genuinely starts to thin. The black hole's mass rests on strong, independently converging evidence, three separate methods landing in the same range. Its exact spin rate, though, the specific fraction of the theoretical maximum it is rotating at, comes almost entirely from working backward through the Blandford-Snagic equations using the jet's observed power output to infer a spin value that would produce it. That is model-dependent in a way. The jet's length and speed are not. You should feel the difference between those two kinds of claims. A photograph of the jet is data. A spin value derived from an equation applied to that data is an inference, built on the assumption that the equation itself correctly describes the physics happening near the event horizon. If some part of that physics works slightly differently than the equation assumes, close enough to a black hole that other effects start mattering, the inferred spin value shifts too. That 9% of a light-year distance is described honestly by the researchers who produced it as an early result, consistent with theoretical prediction, not yet independently confirmed by a second, unrelated method. This is exactly the distinction we drew earlier between predicting something and detecting it directly. Confirming a location is consistent with a model is not the same achievement as pinning that location down with the same confidence we have in the jet's overall length. Decades ago, the exact distance to M87 carried meaningful disagreement between different measurement techniques, some based on the brightness of specific types of stars, others based on entirely different distance indicators. Those methods have since converged, narrowing what was once a real scientific dispute into the 55 million light-year figure we have used throughout this story without hedging. Uncertainty in astrophysics is rarely permanent. It resolves as better instruments and better statistics accumulate, though the resolution can take years or decades to arrive. That history should shape how you hold the launching point measurement and the spin estimate we just discussed. Neither is a permanent gap in human knowledge. Both are open questions actively being worked on right now, using instruments built specifically to push past the current resolution limit, the same way better distance indicators eventually settled the earlier dispute over how far away this galaxy actually sits. There is a broader principle sitting underneath all of this. Science does not treat every claim inside a given field with equal confidence and pretending otherwise, either by dismissing an entire body of research because one part of it remains uncertain, or by treating a provisional model as though it carried the same weight as direct observation. Both distort what is actually known. The honest picture of M87's jet is layered, not uniform. A directly observed, century-confirmed straight line of light. A well-tested mechanism explaining what produces that light. A mathematically recovered true speed and angle, checked against independent predictions. A directly imaged counterjet, confirmed only recently after a century of failed attempts. And, at the innermost edge, a launching point and a spin rate that remain provisional, consistent with theory, awaiting the kind of independent confirmation that settled the distance question decades ago. We are not choosing between certainty and mystery here. We are looking at a single object where different parts of the picture have earned different levels of trust through different amounts of independent testing, and holding all of those levels simultaneously without collapsing them into either false confidence or false doubt is what actually doing this kind of science looks like from the inside. That same layered honesty, applied to something 55 million light-years away, raises a question worth turning towards something far closer. If a structure this well-studied, this heavily instrumented, still carries real uncertainty at its innermost scale, what happens if we take the exact same jet, imagined in a completely different setting, one small enough and close enough that every part of it should, in principle, be easy to picture? Set that beam down inside our own solar system and see how far a supposedly familiar neighborhood would actually have to stretch to contain it. Take everything we just separated into layers of certainty and try a different kind of test on it. Not a test of confidence this time. A test of scale, applied somewhere small enough that you can actually hold the whole picture at once. Set the base of this jet down exactly where the sun sits right now, at the center of our solar system. Not as a metaphor, as a direct substitution, one object standing in for another, so we can walk the same distance we have been discussing in light years and feel it instead in a neighborhood we already carry some intuition for. The jet's launching region, that 9% of a light year we measured in Act 9, would place its innermost structure at roughly 550 astronomical units from the Sun. Pluto orbits at about 40 astronomical units. Even before the jet has finished organizing itself into the coherent beam we have spent this entire story examining, it has already traveled almost 14 times farther than Pluto's entire orbit. The part of this structure still assembling, still chaotic, still not yet a clean line, already dwarfs our solar system's outer edge. Push further out. The heliosphere, the boundary where the sun's solar wind finally loses its fight against the pressure of interstellar space, sits at roughly 100 to 120 astronomical units, depending on direction and on how active the sun happens to be at the time. Voyager 1, the most distant human-made object, crossed that boundary in 2012, after traveling for 35 years. The jet's launching region alone sits nearly 5 times farther out than the edge of the sun's influence. The edge Voyager needed 3.5 decades of continuous flight to reach. Now extend the full length of the visible jet, roughly 12,000 light-years, using that same substitution. Converting light-years to astronomical units multiplies the number by about 63,000. 12,000 light-years becomes something in the range of 750 million astronomical units. The nearest real star to our Sun, Alpha Centauri, sits at about 270,000 astronomical units away. The jet, transplanted into our solar system, would stretch roughly 2,700 times farther than the distance to the nearest star in the actual night sky. A beam launched from one point would already have passed thousands of star systems before reaching its own far end. This comparison earns its place here for a specific reason, not simply because large numbers next to small numbers make for a striking image. It tells you something about scale that the raw light-year figure, on its own, tends to hide. A number like 12,000 light-years sounds impressively large already, and your mind quietly files it under big, without necessarily registering how big relative to anything with texture. Anything you can walk through in your imagination the way you might walk through a solar system you already have some feel for. Placed inside a neighborhood you know, even loosely, the jet stops being an abstract superlative and becomes something closer to a genuine failure of intuition, the kind that only shows up once you force two different scales to sit next to each other directly. Real interstellar space between real stars is not empty in the way this substitution might suggest. It carries thin gas, faint magnetic fields, occasional dust, all of it interacting weakly with anything passing through. The jet's beam, in reality, is punching through a slightly denser, more turbulent version of that same interstellar medium the entire 12,000 light-year length, not through a vacuum with nothing to push back against it. That resistance is part of why the beam eventually loses its coherence at its farthest visible edge rather than continuing to sharpen indefinitely. Distance alone does not explain everything about how this structure behaves. What it travels through matters just as much. A black hole is not a star, and the physics generating this jet has no real analog anywhere inside an actual solar system. The substitution works cleanly for distance, because distance is distance regardless of what sits at either end of it. It works far less cleanly for anything involving gravity, magnetic field strength, or the mechanism producing the beam itself, none of which scale the same way distance does. That limitation does not make the comparison useless. It tells you specifically what the comparison is good for, and what it was never meant to carry. Use it to feel the length. Do not use it to imagine that a black hole behaves anything like a scaled-up star, or that the jet mechanism would work the same way if you actually built a miniature version of it inside a real solar system. Some things translate across scale cleanly. Others do not, and knowing which is part of using an analogy responsibly, rather than letting it run further than the physics actually supports. If this jet reaches lengths that dwarf entire solar systems, and if it has been running continuously for some meaningful fraction of this galaxy's history, then the length itself is not simply a static measurement, frozen at whatever value astronomers happen to record it at. Length, for a structure actively being fed, actively growing outward at close to the speed of light, is also a record of duration. The longer the jet, the longer it has plausibly been running, assuming the launching rate at its base has stayed roughly comparable over that entire stretch. We have measured how far this structure reaches. We have not yet asked, directly and carefully, how long it has actually taken to reach that far, and whether the answer to that question tells us anything about the age of the galaxy hosting it, or about how much of that galaxy's own history this single beam has quietly witnessed from a front-row seat no telescope existed to record until extremely recently. That connection between length and duration deserves a real answer now, not just a question left hanging. If this jet has been actively fed for some meaningful stretch of this galaxy's history, we should be able to work out roughly how long, and the answer changes how you should picture everything we have covered so far. Start with the simplest estimate available. The jet's material moves outward at close to the speed of light, and it stretches roughly 12,000 light-years from base to visible tip. If a single pulse of material had to travel that entire distance at close to light speed, the minimum time required would be somewhere close to 12,000 years. That number, on its own, undersells what is actually happening here, and it is worth being precise about why. 12,000 years is the travel time for one pulse crossing the existing length of the jet. It is not the total time the jet has been active, because the launching point has presumably been firing material continuously, or in episodes, the entire time the beam has existed, not just once at some single moment in the deep past. Independent estimates, built from studying how the jet's radio and X-ray emission has evolved, and comparing that to models of how long a magnetically confined outflow like this one can remain collimated before losing coherence, place the jet's total active lifetime somewhere in the range of 1 million to a few million years. Some researchers, working from the size and structure of the surrounding radio lobes, the vast clouds of aged particles the jet has been depositing into intergalactic space over its lifetime, push that estimate even further, into the tens of millions of years. Put size. Modern humans, anatomically similar to the people alive today, have existed for roughly 300,000 years. Even the more conservative estimate for this jet's active lifetime, 1 million years, is more than 3 times longer than our entire species has existed. The more generous estimate, tens of millions of years, stretches that comparison so far that human existence becomes a rounding error against it. M87 itself, the galaxy hosting this black hole, formed in the early universe, likely within the first few billion years after the Big Bang, making it one of the older large galaxies astronomers have studied in detail. The galaxy's total age runs into the range of 10 to 12 billion years. Set the jet's estimated lifetime, even at the high end of tens of millions of years, against that 12 billion year galactic age, and the jet has been running for something on the order of 1/10 to 1% of the galaxy's entire existence. Not the whole story of this galaxy, a chapter within it, though a chapter substantial enough to leave a permanent structural mark. You can feel a rough, honest version of that ratio using something closer to home. Picture a person who has lived to be 80 years old and imagine one specific habit or relationship that lasted somewhere between 1 month and 10 months of that entire life. Brief, relative to the whole span, and yet potentially significant enough, depending on what it was, to leave a lasting mark on everything that came after it. The jet occupies a similar kind of window inside M87's full history, brief relative to the whole, substantial enough to matter regardless. This raises a specific. If the jet has been running for something on the order of 1 million years or more, what happens to it if the fuel source, the energy drawn from the black hole's spin, were to weaken or stop entirely? The answer follows directly from the synchrotron cooling mechanism we worked through. If the black hole stopped feeding new energy into the magnetic field tomorrow, the jet would not vanish instantly. The material already in flight, already moving outward at close to light speed, would continue traveling, continue radiating, continue cooling, exactly the way the individual knots we discussed have been cooling and dimming across the Chandra time-lapse. The brightest, most energetic sections would fade within years to decades. The dimmer, lower energy sections, farther from the black hole and already cooler, would persist for centuries or longer, gradually losing coherence as the confining magnetic field, no longer actively maintained, slowly relaxes and lets the beam disperse into the surrounding intergalactic gas. The radio lobes surrounding M87, the large diffuse clouds of aged particles extending far beyond the visible jet itself, show internal structure consistent with multiple distinct episodes of activity separated by quieter periods, rather than one single continuous outburst running unbroken for the jet's entire lifetime. If that interpretation holds up under further study, this jet has possibly switched on, weakened, and switched on again, more than once, over its history, each episode potentially separated by intervals long enough for earlier material to cool substantially before a fresh pulse of energy arrived to reinvigorate the beam. The evidence for multiple episodes comes from analyzing the structure of aged, diffuse radio emission, a more indirect measurement than the direct imaging techniques confirming the jet's length or the counterjet's existence. It remains a genuinely live area of research, one where different groups studying the same radio lobes have not yet reached full agreement on exactly how many distinct episodes the data actually supports. What stays solid, regardless of how that specific debate resolves, is the core picture this act has built. This jet is not a single uninterrupted event stretching back to some fixed moment in the deep past. It is closer to an ongoing relationship between a black hole and its own magnetic field, one that has likely waxed and waned, possibly paused and restarted, across a stretch of time longer than our species has existed, inside a galaxy that was already ancient before this particular chapter of its story began. We have now placed this jet's lifetime against the galaxy hosting it and against the whole of human history for comparison. What remains is a harder, more specific question about our own place inside that comparison. Not how long the jet has existed, but how much of that existence a species capable of building telescopes has actually had the chance to witness, and what that ratio should tell us about how much confidence to place in any single human generation snapshot of an object this old. Let's put an honest number on that ratio, because the answer is smaller than most people would guess before doing the arithmetic. Human beings have been capable of pointing an instrument at the sky and recording what they saw for a little over 400 years, starting with the first telescopes in the early 1600s. Radio astronomy, the specific tool that eventually revealed the counterjet and the launching structure we discussed earlier, has existed for less than a century. Set either number against the jet's estimated active lifetime, somewhere between 1 million and several tens of millions of years, and the fraction of that lifetime humans have actually observed comes out to somewhere between 1/100th of 1% and 1/10,000th of 1%. Numbers that small resist intuition almost as badly as numbers that large do, so give this one a shape you can actually hold. Imagine the jet's entire active history compressed into a single continuous film, 24 hours long, playing from the moment it first switched on to this exact night. Every act of this story, every measurement, every photograph from Curtis in 1918 to Chandra's most recent pass in 2025 would occupy less than a single second of that 24-hour film. Less than 1 second out of an entire day. Every measurement of speed, every estimate of mass, every claim about how the jet's brightness has changed, all of it comes from watching roughly 1 second of a 24-hour film and drawing conclusions about the whole day from it. This is not a criticism of the science. It is simply the actual size of the window human instruments have had to look through. The jet's overall length, its viewing angle, its rough speed. These are structural features that would look essentially the same whether you sampled that 1 second from early in the film or late in it, because the underlying geometry, set by the black hole's mass and spin, changes on timescales far longer than even the jet's full multi-million-year lifetime. Structural measurements survive a short viewing window intact. The variable brightness we tracked through the Chandra time-lapse is a different category of claim entirely, and it deserves to be treated with the caution that category demands. A single second, however carefully observed, tells you almost nothing reliable about the full pattern of a day-long film's changes in lighting, pacing, or mood. It tells you only that change happened during that second, and roughly how fast. Whether that particular second was typical or unusual, whether it caught the film during a calm stretch or a dramatic one, is a question the 1 second of footage cannot answer on its own. Walk into a room where two people are having a conversation. Catch 30 seconds of it and walk back out. You now know something real. That a conversation is happening, roughly what tone it carries. Maybe a fragment of subject matter. You do not know whether those 30 seconds represent the entire arc of the conversation, its opening, its climax, or its resolution. 30 seconds inside a much longer exchange carries genuine information and genuine limits simultaneously, and both of those things are true at once. The Chandra time-lapse occupies exactly that position relative to the jet's full multi-million-year history. Real information, genuinely observed, carrying real limits on what it can tell you about the pattern as a whole. If this jet really has switched on and off multiple times across its history, as the structure of the surrounding radio lobes suggests it might have, then the entire span of confirmed, careful human observation, 400 years of telescopes, less than a century of radio astronomy, sits inside what might be only the most recent of several such episodes. Everything this story has described as the jet's behavior might describe one chapter of a longer, repeating story, not the story's complete shape. This is not a reason to distrust the measurements we have already covered. It is a reason to hold them at the correct scale. The same discipline Act 13 asked you to apply to distinguishing direct observation from model-dependent inference, applied here to a different axis entirely, the axis of time, rather than the axis of certainty. Consider what this means for how astronomy as a discipline actually operates, working under a limitation this severe. Every long-lived astronomical object, not just this one, gets studied through a viewing window that is, in cosmic terms, essentially instantaneous. The entire body of modern astrophysics, every model of stellar evolution, every theory of galaxy formation has been built by watching processes that unfold over millions or billions of years, using an observational record spanning at most a few centuries. Astronomers have learned to build reliable knowledge anyway, not by pretending the short window is longer than it is, but by combining many different objects at many different stages of their own individual histories, using one galaxy's early stage to infer what another galaxy's later stage might look like, assembling something like a full story out of many overlapping brief glimpses. M87's jet benefits from exactly that kind of comparative approach. Other galaxies host jets too, some younger, some apparently older, some clearly in the middle of a fresh outburst, others showing the faded, extended radio lobes consistent with a jet that has already switched off. Comparing this jet's current state against that broader population lets astronomers place it somewhere inside a likely life cycle, even without having watched any single jet complete that entire cycle from start to finish within the span of human observation. That comparative method does not eliminate the limitation this act has been describing. It works around it, the same way you might reconstruct a stranger's entire life story by interviewing many different people at many different ages, none of whom you watched grow up personally, but whose overlapping accounts, pieced together carefully, add up to something close to a complete picture. We have now measured this jet's structure, tracked its energy source, confirmed its hidden twin, and honestly reckoned with how small a sliver of its full history any human instrument has actually witnessed. What remains is a question this story has been circling since the very first act, without ever asking it plainly. If human observation is this brief, this limited, relative to the object being observed, does that same limitation apply to something much closer than 55 million light-years away, something inside the very body doing the observing? Every measurement in this story has depended on light needing time to travel, and on an observer receiving that light later than the event it describes. Your own nervous system runs on a version of the exact same principle at a scale small enough to live inside a single body. Touch something sharp with your fingertip, and you do not feel the pain at the instant your skin makes contact. A nerve signal has to travel from the fingertip through the arm, into the spinal cord, and up into the brain, along a path made of specialized cells called neurons, each one passing an electrical and chemical signal to the next in a relay, rather than a single instant transmission. That relay is not instantaneous, and the delay it introduces is measurable, not philosophical. Signals traveling along the fastest, most heavily insulated nerve fibers in the human body move at roughly 120 meters per second. Signals traveling along thinner, less insulated fibers, the kind carrying certain types of pain and temperature information, move closer to 1 meter per second. Do the arithmetic on your own arm. A nerve signal from your fingertip to your brain, traveling along the faster class of fiber, takes somewhere around 10 to 20 milliseconds to arrive. Along the slower fiber type, carrying a duller, later wave of pain that often follows the sharp initial jolt, the same trip can take a fifth of a second or more. You experience touching something sharp as one seamless moment. It is not one movement. It is at least two separate signals, arriving at two separate times, stitched together by your brain into something that feels instantaneous only because the gap between them is too small for conscious attention to catch. Every knot of light along that beam left its source at a different point in the past, and your eye receives all of it bundled into a single photograph that feels momentary despite containing thousands of years of layered delay. Your own hand, touching a hot stove, sends signals that arrive at your brain seconds apart in some cases, bundled by your own nervous system into a single sensation that feels like one continuous event. Neither case involves an illusion in the sense of something false. Both involve integration, a real, physical assembling of separately timed information into an experience that feels unified because the assembling itself is fast and automatic, hidden from anything you could consciously catch happening. The visual system carries its own version of exactly this delay, one that most people never think about because it never causes a practical problem. Light entering your eye triggers a chemical reaction in the retina, which then has to be converted into an electrical signal and relayed through several layers of neurons before reaching the visual cortex, the part of the brain that actually assembles a conscious image. That entire chain takes somewhere between 50 and 150 milliseconds, depending on the brightness and complexity of what you are looking at. Everything you see, right now, in the room around you, is a reconstruction of light that struck your retina up to a tenth of a second ago. You are never perceiving the present moment directly. You are perceiving a very recent, carefully assembled past every single second of your waking life, without exception. This is the same fundamental structure as the 55 million year gap separating you from the jet, compressed down to a tenth of a second instead of tens of millions of years. The mechanism is identical, only the scale differs. Light, or signal, needs time to travel. The receiving system needs additional time to process what arrived. What you experience as now is always, in both cases, a reconstruction of something slightly older. There is a specific consequence of this delay that neuroscientists have studied directly, using reaction time experiments, and it deserves to be named because it changes how confidently you should trust your own sense of causing your actions in real time. Studies measuring the gap between a decision to move and the actual electrical signal initiating that movement in the brain have found that measurable neural activity related to a choice can be detected before a person reports consciously deciding to act. This remains a genuinely debated area of neuroscience, and the interpretation of exactly what those measurements mean for questions about free will stays unsettled among researchers who study it closely. What is not seriously disputed is the more basic finding underneath the debate. Conscious awareness of an action lags slightly behind the neural processes generating that action. The same basic pattern as light lagging behind the event that produced it, just measured in a completely different system, using completely different instruments. Consider what this means for the entire story. We have been building around an object 55 million light-years away. One idea has kept returning in different forms. Distance and delay shape what any observer can know. Even a black hole's own light has to travel before anyone can measure it, and even the fastest instruments on Earth capture only a tiny fraction of a much longer, largely invisible history. None of that turns out to be a special property of cosmic distances. It is a property of information itself, of how anything, anywhere, at any scale, has to physically travel and be processed before it becomes knowledge to someone receiving it. The jet's 55 million year delay and your fingertips' 20 millisecond delay are the same phenomenon, wearing two very different scales. That recognition changes something about how this whole story should feel. None of this was ever just about black holes or distant galaxies. It has been pointing towards something far more fundamental. Every act of perception is shaped by delay. Every piece of information arrives after the event that created it, including this sentence, reaching you a fraction of a second after it left whatever produced it. We have now traced this same principle from a beam 55 million light-years away down into the wiring of your own body. What remains is the question this entire story has been quietly building toward since the very first photograph in 1918. After stripping away every illusion of speed, every hidden twin, every gap between seeing and knowing, what is actually left standing? Once all of that has been accounted for and set aside, let's actually take stock of what survives once every layer of illusion and every limitation on observation has been accounted for, rather than letting the accumulation blur into a general feeling of uncertainty. Start with the piece that looked most dramatic and turned out to be the least physically real. The 5 times light speed motion measured inside this jet was never a violation of anything. It was the geometry of a fast-moving source angled close to our line of sight, and once you correct for that angle, the true speed settles at roughly 99% of light speed, extraordinary on its own terms, but fully compatible with everything relativity requires. That correction matters beyond simply fixing one number. It tells you that the jet's true physical speed has been sitting there the whole time, unchanged by how we happen to be looking at it. Our angle distorted the measurement. It never touched the underlying reality generating that measurement in the first place. Move to the second layer, the one that stayed hidden for the better part of a century rather than merely appearing distorted. The counterjet was never absent. It existed the entire time the visible jet did, launched by the same rotating black hole, along the same magnetic axis, carrying roughly the same physical process in reverse. What kept it invisible was relativistic dimming, the same underlying physics that inflated the visible jet's apparent speed, working in the opposite direction on the side moving away from us. Here again, the illusion was never in the object. It was in the relationship between the object's motion and our position relative to it. Change the wavelength, as James Webb eventually did, and the counterjet stops hiding, because infrared light survives the journey with less of the penalty that suppressed it at shorter wavelengths. Nothing about the counterjet changed to become visible. Our instrument changed to finally catch what had been there the entire time. The third layer sits differently from the first two, because it was never really an illusion at all. It was a genuine boundary. The exact point where this jet transitions from chaotic infalling material into a coherent, collimated beam remains, even now, at the edge of what any instrument on Earth can resolve. That is not something correcting for an angle or switching a wavelength fixes. It is a real limit, imposed by distance and by the physics of how sharply any telescope can focus, and it will only move as instruments themselves improve. 2 of the 3 obstacles standing between us and a clear view of this jet turned out to be properties of observation itself, correctable once the correcting mechanism was understood. The third obstacle is different in kind, a genuine frontier rather than a solvable distortion. That distinction matters for how confidently you should now describe this object, because it lets you separate what is settled from what is still open, cleanly, without either overclaiming certainty or drowning the entire picture in unnecessary doubt. Here is what stands as settled, checked across multiple independent lines of evidence, robust to every correction applied so far. A black hole with a mass of roughly 6.5 billion suns is extracting energy from its own rotation through a twisted magnetic field, launching two symmetric beams of relativistic particles along its spin axis, one aimed close enough to our line of sight to appear both extremely bright and superluminally fast, the other aimed away from us and correspondingly faint. That beam has remained pointed in essentially the same direction for over a century of direct observation, and probably far longer than that, held stable by the sheer rotational inertia of an object too massive for the galaxy's ordinary turbulence to meaningfully disturb. Along its length, the beam is not static. Individual patches of it brighten and dim on a timescale of years, driven by how quickly the electrons producing that light cool as they radiate away their own energy. None of that core picture is threatened by anything raised in the axe examining illusion and limitation. If anything, the illusions, once explained, reinforce the underlying picture rather than undermining it. The superluminal motion makes sense only if the true speed and angle are what independent measurements say they are. The counterjet's faintness makes sense only if the same relativistic beaming mechanism inflating the visible jet's brightness is real and operating exactly as described. Discovering that something looked different than it actually was does not weaken your confidence in the underlying physics. It strengthens it, because the illusion itself only exists in this specific shape if the physics generating it is correct. A wrong model would not produce a 5-time superluminal measurement that matches, to within observational error, exactly what the equations predict for a source moving at 99% of light speed at an angle of 14 to 20 degrees. That precision of agreement is not something a flawed understanding of the mechanism could produce by accident. The exact distance from the event horizon where chaos becomes order. The precise spin rate of the black hole itself, currently inferred rather than directly measured. Whether the radio lobes really do record multiple distinct episodes of activity, separated by quiet periods, or a single continuous outburst whose apparent structure comes from something less dramatic. Holding both of those categories at once, without collapsing one into the other, is not a compromise or a hedge. It is the actual, accurate shape of what a century of careful observation has produced. Most of the structure is understood well enough to trust completely. A specific, identifiable piece of it sits right at the frontier where current instruments run out of resolving power, waiting for whatever comes after the Event Horizon Telescope and James Webb to push that boundary further inward. We have now assembled the full mechanical picture of this jet, layer by layer, illusion by illusion, all the way down to the honest edge of what remains unresolved. What that picture has not yet answered is a different kind of question entirely, one that has nothing to do with resolving power or wavelength or viewing angle. Why any of this, 55 million light-years away, watched for barely a sliver of its own long history, should matter to someone lying in a dark room on a small planet orbiting an ordinary star, listening to all of it unfold? Why should any of this matter to you, specifically, lying in a dark room on an ordinary planet, orbiting an ordinary star, 55 million years removed from the light currently reaching your eyes if you happen to look up? Start with the most direct answer. This story never asked you to care about M87 because it is large or violent or record-breaking. It asked you to notice something about how observation itself works, using an object extreme enough to make that mechanism visible in ways a smaller, gentler phenomenon never could. Every distortion this jet has revealed turned out to be a distortion in the relationship between an observer and what they are observing, not a flaw in the object itself. The superluminal motion existed only because we happened to be viewing a fast-moving source from a particular angle. The counterjet remained hidden only because relativistic beaming suppresses light traveling away from a given observer. Someone else, standing somewhere else in the universe and looking at this very same black hole from a different direction, would see an entirely different asymmetry. Perhaps even the opposite jet, shining brightly while the one we see so clearly faded into the background. That detail is worth pausing on directly. There is no single universal answer to how bright each side of this structure appears, how fast its features seem to move, or even which side looks more dramatic. Those properties depend on where you happen to be standing when you ask the question. What stays fixed, independent of any observer's position, is the underlying physics generating both beams equally: the mass, the spin, the magnetic mechanism extracting energy from rotation. The appearance changes with the observer. The mechanism does not. You do not experience the world directly. You experience a reconstruction, assembled from signals that travel different distances at different speeds, arriving at your brain already late by the time conscious awareness catches up to them. Two different people, standing in two different positions, watching the exact same event, would receive slightly different versions of it, shaped by their own distance, their own angle, their own nervous system's particular processing delays. This is not a flaw specific to human perception, and it is not a flaw specific to studying black holes from Earth. It is what observation itself requires, everywhere, at every scale, whenever information has to travel from a source to a receiver before it can become knowledge. The universe does not hand any observer anywhere, a view from nowhere. Every view comes from somewhere specific, and that specific position always shapes what gets seen. Consider what this means for how you should hold confidence itself, not just about M87, but about anything you observe carefully enough to notice its own limitations. Confidence does not require a view from nowhere. It requires understanding your own position well enough to know what that position is doing to what you are seeing. The same correction astronomers applied to recover a true speed from an inflated one, the same correction that let James Webb catch a jet that visible light alone had been hiding for a century. That correction is available to you too, in a much more ordinary sense, whenever you notice that your own vantage point, your own history, your own habits of attention are shaping what you take to be simply true rather than simply how things look from where you happen to be standing. The discipline this jet has been teaching, across 18 acts, is not really about telescopes. It is about the difference between what arrives and what actually happened, and the patient work required to recover the second from the first. This jet is not one settled fact. It is a layered structure of certainty and uncertainty, direct observation sitting beside careful inference, sitting beside genuine, unresolved frontier, most extended understanding of almost anything complex enough to be worth studying, has exactly this same layered shape. The instinct to want a single, clean, fully settled answer, free of any remaining uncertainty, is understandable. It is also not how careful understanding of anything difficult actually works, whether the subject is a black hole 55 million light-years away or something far closer, far more personal, sitting inside your own life right now. Some parts settle. Some parts remain open, genuinely, honestly open, not as a failure of the effort but as an accurate reflection of where the boundary of current knowledge actually sits. Holding both of those categories at once, without collapsing one into the other, without pretending the open parts are settled or dismissing the settled parts as equally uncertain, is not a compromise. It is what taking something seriously actually looks like, once you have spent enough time with it to know the difference. This is the last idea this story needs from the sky before turning fully back toward you. Everything measured across 19x, the length, The speed, the mass, the mechanism, the hidden twin, the uncertain edge, all of it describes one specific object, seen from one specific position, at one specific narrow window in its own much longer history. That specificity is not a limitation to apologize for. It is the only way anything gets known at all, by anyone, anywhere, looking at anything. We have spent this entire story learning to distrust a first impression, to ask what angle, what delay, what mechanism might be shaping what we thought we were seeing directly. That same discipline, applied gently, without turning into suspicion of everything, is available to you the next time something in your own life looks obviously one way and turns out, on closer inspection, to be something slightly different once you account for your own position relative to it. What remains, after correcting for angle, for delay, and for the narrow window of human observation, is not a bigger mystery than the one we started with. It is a smaller, steadier one, close enough now to bring all the way home from 55 million light-years away to the exact room you are lying in, and the exact body doing the listening. 55 million years of light, 5 times the speed limit that turned out not to be a limit at all, a second beam hidden by nothing more than an angle, and a beginning still too small for any telescope to touch. All of it traced back, across 19 acts, to one simple exchange. A black hole gives up a little of its own spin, and in return, something is thrown outward, fast, organized, and far. That exchange is not exotic. It is not confined to black holes, or to galaxies, or to anything 55 million light-years from where you are lying right now. You are breathing. Somewhere in your chest, a muscle is contracting, pulling air into 2 lungs built from tissue that folds and unfolds without you directing a single motion of it. That contraction takes energy. The energy comes from oxygen, carried to your muscle cells by blood, and inside those cells, mitochondria are converting chemical bonds into the specific kind of usable energy your body runs on. Follow that conversion down to where it actually happens, at the molecular scale, and you find something that would look familiar to anyone who just spent 19 acts learning how M87’s jet works. Electrons, moving through a chain of proteins embedded in a membrane, releasing small amounts of energy at each step, that energy captured and used to pump other particles across that same membrane. A gradient builds. Particles piling up on one side of a barrier, held there by that gradient the same way a dam holds water back, storing potential energy in the simple fact of an uneven distribution. Then the gradient releases. Particles flow back across the membrane through a specific channel, a molecular turbine, spinning as they pass through it, and that spin, that literal, physical rotation of a molecular machine, is what generates the energy your cell actually uses to do anything at all. A spinning structure, extracting usable energy from a flow moving past it. That energy then directed outward to do work somewhere else in the system. That is the mechanism inside every living cell in your body, right now, thousands of times a second, in nearly every one of the trillions of cells keeping you alive tonight. It is also, in its bones, the same physical shape as the mechanism spinning a magnetic field around a black hole 6.5 billion times heavier than the sun, not a metaphor stretched to fit. The same underlying principle, rotation converted into directed energy, showing up at 2 scales separated by more orders of magnitude than most numbers can comfortably describe. You do not need to remember the name of that molecular turbine, ATP synthase, to carry the deeper point out of this story with you. The point is simpler than the vocabulary. The universe appears to have a small number of ways it knows how to move energy from one place to another, and it reuses those ways relentlessly, from the spin of a supermassive black hole down to the spin of a molecular machine sitting inside a single cell in your own diaphragm right now. Feel your own chest rise once, slowly, if you want to notice this directly rather than simply hearing it described. That single breath required billions of these molecular turbines spinning in near-perfect synchrony across the muscle tissue doing the work, each one converting a gradient into motion, each one following the same basic logic as a magnetic field wound tight around a black hole's spin, just scaled down until it fits inside something smaller than a single human cell. There is a kind of company in that, if you let yourself notice it rather than reaching past it toward something larger. The same physics holding this jet stable for over 1,000,000 years is, at this exact moment, keeping you breathing steadily enough to fall asleep. Nothing about that connection needs you to feel small. The comparison this story built, from the very first act, was never really about size. It was about recognizing the same handful of mechanisms wearing different scales, the same rotation, the same gradient, the same conversion of one kind of energy into another, showing up again and again, wherever the universe needed to move energy from where it was stored to where it was needed. You have spent this entire night tracing one particular version of that mechanism outward, 55 million light years, through illusion after illusion, correction after correction, until only the honest shape of it remained. That shape turns out to live inside you too, quietly, continuously, asking nothing of your attention to keep working. Let your breathing settle into whatever rhythm it wants to find right now. You do not need to think about the mitochondria, or the gradient, or the turbine, for any of it to keep running exactly as it has been running this entire time, since before you started listening tonight, and for every night you have ever fallen asleep before this one. The jet in M87 will still be there tomorrow, still 5 times faster than it should be able to be, still hiding half of itself from most of the universe, still waiting for whatever comes after James Webb to finally see the last few hundred astronomical units nobody has reached yet. You will still be here too, breathing the same way, the same mechanism turning quietly in the dark, asking nothing else of you tonight. Thank you for spending this time with something this far away, and for letting it lead you, eventually, back to something this close. Sleep well.